Welcome to our exploration of statistical mechanics, a branch of physics that connects microscopic behaviors to macroscopic properties. In this video, we'll break down key theories, their strengths, and their limitations. Statistical mechanics is fundamental for understanding phenomena like phase transitions, energy distributions, and the behavior of complex systems. We'll start by introducing the concept of free energy and its importance, then move on to discuss the variational principle, and finally examine the limitations and applications of various physical theories. By the end, you'll have a clearer picture of how these theories shape our understanding of the physical world. Helmholtz free energy, denoted as F, is a central quantity in statistical mechanics. It is related to the partition function, Z, through the equation Z equals E beta F, where beta is the inverse temperature. This relationship allows us to connect thermodynamic properties with statistical ensembles. Understanding this equation is crucial for analyzing how systems exchange energy and reach equilibrium. The partition function encapsulates all possible states of a system, making it a powerful tool for predicting behavior under various conditions. Let's delve deeper into how this equation forms the foundation for further theoretical developments. In statistical mechanics, the density matrix, represented as ρ, plays a pivotal role in describing the statistical state of a system. By leveraging properties of the density matrix and entropy, we can derive important inequalities that govern system behavior. Entropy measures the disorder or randomness within a system, and its relationship with the density matrix helps us understand how systems evolve toward equilibrium. These concepts are not only theoretical, but also have practical implications in fields like quantum mechanics and thermodynamics. Using the properties of the density matrix and entropy, we derive the variational principle for free energy. The inequality F less or equal to H rho plus T tr rho ln rho shows that the actual free energy is always less than or equal to the trial free energy calculated from any density matrix. This principle is powerful because it provides a method to estimate the minimum free energy, which is a key factor in determining the stability and equilibrium of physical systems. The trial free energy, Fρ, incorporates both the average energy and entropy contributions, making it a comprehensive measure. The trial free energy, Fρ, is defined as Tr rho H plus T Tr rho ln rho. This formula combines the average energy of the system, calculated using the density matrix, and the entropy term, which accounts for the disorder. By evaluating Fρ for different density matrices, we can estimate the minimum free energy and predict the most stable configuration. This approach is widely used in both classical and quantum statistical mechanics to analyze complex systems and their thermodynamic properties. Variational principle asserts that the actual free energy is always the minimum value among all possible trial free energies. This means that physical systems naturally evolve toward configurations that minimize their free energy. This principle is fundamental for understanding equilibrium states and predicting how systems respond to changes in temperature, pressure, or other external factors. It also underpins many computational methods used in modern physics and chemistry. Landau theory provides a framework for understanding phase transitions, such as changes from solid to liquid or liquid to gas. It introduces the concept of an order parameter, which describes the degree of order in a system. However, Landau theory has limitations. It can only be applied when the order parameter is uniform and small, and it is not suitable for situations far from the critical point. Despite these constraints, Landau theory remains a valuable tool for analyzing phase transitions near the critical temperature. A Landau theory is effective near the critical point. It cannot be applied when the order parameter is non-uniform or large. Additionally, its predictions become unreliable far from the critical temperature. These limitations mean that Landau theory is best used for systems undergoing continuous phase transitions, where changes are gradual and the order parameter remains small. For more complex scenarios, alternative theories are required to accurately describe system behavior. Mean field theory simplifies complex interactions by averaging the effects of all particles in a system. While this approach makes calculations easier, it comes with precision issues. For example, MFT predicts a critical exponent beta equals 0.5, but actual values are typically around 0.3 to 0.4. This discrepancy highlights the limitations of MFT, especially when dealing with systems near critical points. Despite its shortcomings, MFT remains a widely used tool in statistical mechanics, particularly for magnetic systems. Bragg-Williams theory, a form of mean field theory, is primarily used for magnetic systems. It can be applied at all temperatures, including near zero. However, it cannot be extended to models with symmetries other than the simple up-down Ising symmetry. This limitation restricts its applicability to a narrow range of systems, but within its scope, Bragg-Williams theory provides valuable insights into phase transitions and magnetic behavior. Phase transitions, such as solid-liquid or liquid-gas changes, are central topics in statistical mechanics. Landau theory and mean field theory both provide frameworks for understanding these transitions, but their applicability varies. Landau theory is most effective near the critical temperature, while mean field theory offers broader but less precise predictions. Understanding the strengths and limitations of these theories helps us choose the right approach for analyzing different types of phase transitions. Variational mean field theory is an advanced approach that overcomes some limitations of standard mean field theory. By optimizing the trial-free energy, this method provides more accurate predictions for systems near critical points. It combines the strengths of variational principles with the simplicity of mean field theory, making it a powerful tool for analyzing complex systems. This approach is especially useful in modern research, where precision is essential. Despite its limitations, Bragg-Williams theory is valuable because it helps us understand phase transitions in two very different areas of physics. For example, it explains the transition from ferromagnetic to paramagnetic states in the Ising model, as well as the transition from ordinary to black hole phases in gravity. These applications demonstrate the versatility of Bragg-Williams theory and its importance in both classical and modern physics. The Ising model is a classic example where Bragg-Williams theory is applied. It describes the transition from ferromagnetic to paramagnetic states, which is a second-order phase transition. The order parameter in this case is magnetization, which measures the degree of alignment among magnetic moments. Understanding this transition is crucial for studying magnetic materials and their properties. Bragg-Williams theory also applies to gravity, specifically in the transition from ordinary phases to black hole phases. This is a first-order phase transition, with the order parameter being the horizon radius. Such applications highlight the theory's ability to bridge concepts across different fields, from condensed matter physics to astrophysics. By understanding these transitions, we gain deeper insights into the nature of black holes and the fundamental laws governing the universe. In summary, statistical mechanics offers powerful theories for understanding phase transitions and equilibrium states. While Landau theory, mean field theory, and Bragg-Williams theory each have their strengths and limitations, Advances like variational mean field theory continue to improve our predictive capabilities. By recognizing the scope and constraints of these theories, researchers can select the most appropriate tools for their studies. As we continue to explore new phenomena, statistical mechanics remains a cornerstone of modern physics.